The Elastic Continuum Theory models the vacuum as the plenum, a continuous elastic medium maintained under extreme tension. In this framework, subatomic particles are physical distortions within this underlying structure. This is the foundation of the ECT framework. While current models often treat particles as zero-dimensional points, ECT defines them as stable solitonic wave configurations. These are three-dimensional structures sustained by the continuous elastic feedback of the medium itself. This creates a specific mechanical challenge. A perfectly continuous and unbroken medium must somehow give rise to the strictly quantized discrete particle masses we measure in the laboratory. To trace how this happens, we will dissect the master equation governing vacuum stability, plot the resulting theoretical mass-energy spectrum, and map known particles against it to measure where empirical data diverges from the predicted curve. This shift in perspective moves the focus away from isolated particles to the nonlinear feedback dynamics of the space they occupy. Within ECT, mass energy across all scales is governed by a single mathematical baseline. This is the calibrated master equation. The output variable, E, represents the final discrete mass-energy stability point for a given configuration. The leading coefficient, K, defines the vacuum stiffness constant, the base resistance of the continuous medium. The integral term immediately following K calculates the core solitonic energy of the localized wave. It evaluates the squared gradient of spatial deformation, measuring the strain on the vacuum across an infinite continuous space. Calculating tension across infinite space leads to infinite energy states. Physically, the vacuum needs a boundary condition to constrain the energy into a finite limit. That boundary is provided by the right-hand side of the equation, a nonlinear logarithmic correction term. Within this term, alpha acts as the nonlinear coupling coefficient, and sigma 0 serves as the critical reference scale, calibrated to the localization radius of the electron. This correction block models the elasticity and internal feedback loop of the plenum. Because the feedback is logarithmic, it acts as a spatial filter. It restricts localization radii, represented by sigma, forcing waves into specific permissible physical states. The vacuum's elastic boundary conditions physically dictate where mass can and cannot exist, naturally producing a quantized distribution of energy. We can apply this equation across the entire scale of the universe to see the resulting energy distribution. This chart maps out that coordinate space. The y-axis tracks mass energy in giga-electron volts, while the x-axis tracks the structural localization radius in meters. Evaluating the master equation across continuous radii generates this optimized master curve. The curve reveals a strict inverse log-linear relationship. As the structural scale of a distortion shrinks, the energy required to sustain it scales exponentially. While the continuous line represents the mathematical range, the elastic medium only maintains stability at specific harmonic intervals. These intervals act as eigenresonance nodes, where wave configurations lock into permanent stability. Plotting these nodes yields 12 theoretical resonance states derived directly from the theory. The spectrum spans a massive physical scale, beginning with node 1 on the top left. Node 1 is situated at the Planck scale, with a localization radius of roughly 10 to the negative 33 meters, and a mass energy of 10 to the 21st giga-electron volts. From there, the theoretical nodes step down the curve in a rhythmic sequence. Each node is separated by predictable, exact orders of magnitude along the log scale. As we move further down into the microscopic realm, we reach nodes 6, 7, and 8. Node 8 sits at a radius of 10 to the negative 17th meters, marking the threshold of the TeV scale. These nodes represent the near-future collider's limit, bridging abstract cosmology with testable high-energy particle physics. With a range spanning 54 orders of magnitude, the master equation establishes a consistent theoretical baseline for the vacuum's resonance states. Testing this baseline requires comparing it against empirical data from modern colliders. This is the result when we map the 7 known standard model particles over the ECT curve. We can see a distinct clustering of the top quark, the Higgs boson, and the Z and W bosons. These particles occupy a narrow localization radius between 10 to the negative 14th and 10 to the negative 15th meters. While the standard model particles follow the downward slope of the continuum, they do not align with the rhythmic geometric spacing of the nodes. Instead, they bunch together in localized clusters. This clustering suggests the presence of complex symmetry-breaking dynamics. In empirical reality, these forces push particle masses away from the predicted harmonic alignment. We see this divergence most clearly at the bottom right of the graph. The electron is located at a radius of 3.86 times 10 to the negative 13 meters, the very reference scale, sigma 0, used for the master equation. Yet the data shows that the electron exhibits the most significant physical deviation from the optimized master curve. This creates a paradox. The particle used to calibrate the vacuum's elasticity is the one that shows the greatest overall divergence from the theoretical trajectory. While the large-scale vacuum follows strict geometric rules, local particle feedback loops introduce heavy anomalies that disrupt the predicted symmetry. The ECT framework provides a broad predictive range, but its limits are exposed by empirical data. Looking at the full map of the spectrum, the tension between theory and observation is clear. The master equation successfully bounds the theoretical mass limits of the universe, from the Planck scale down to modern collider thresholds. However, the clustering of heavy bosons and the isolation of the electron show that mathematical harmonics alone cannot account for all physical deviations. A comprehensive model of vacuum physics must account for both the rigid mathematical harmonics of the plenum and the asymmetrical symmetry breaking observed in matter. The challenge remains in characterizing these specific nonlinear deviations to bridge the gap between continuous vacuum mechanics and the observed standard model.